Hello APC Mechanics students in Unit 5 Rotation, Class 8, 5.3 Atwood Machine again, Part 2. Then Section 1, recap for the Atwood Machine. Now we're gonna review what we have done in the previous class. In the previous class, we have seen the acceleration for a massive Atwood machine of moment of inertia I and radius r, which is A as a fractional mass multiplied by g, in which the injected mass appears as an inertial mass in the denominator in the form of I over r square. And this result can be anticipated by the interpretation. Taking a step backward, let's recall the acceleration for a massless Atwood machine, and it's given by a fractional mass factored by gravitational acceleration g. The fractional mass can be understood as the numerator and denominator. The numerator represents an algebraic sum of masses. Masses helping the motion would be preceded by a plus sign. Masses opposing the motion would be preceded by a minus sign. The denominator is inertial mass or absolute sum. All masses involved in the system will be added positively in the numerator, and this reflects a law of nature, which means that acceleration always increases and doesn't decrease. How this key concept, the fractional mass, can be implemented to generalize for a massive pulley. So now we have changed from being massless to being massive. If a new mass I over r square is injected to the system, so why I over r square represent a mass? Because I is proportional to kg and r square. So if we divide by r square, then this quantity would be proportional to mass. This mass should be appear where the denominator, the numerator, or both. For sure it will appear in the denominator, since there we place the masses of all the system. However, this mass is neither helping nor opposing the motion, because it's being symmetrically distributed among the pulley. We assume for this reason it won't ever affect the expression of the numerator. After modification, the result would be given by the following. If the pulley is a hoop, we know that the inertia of a hoop is given by mr square. Replacing in the expression of the acceleration, we would get now mr square divided by r square, that would be m. So it's given by fractional mass m2 minus m1 over m1 plus m2 plus m multiplied by g. Then the acceleration of an Atwood machine, the hoop, is given by the following. If the pulley is a disk, then the moment of inertia is given by half mr square. Replacing in the expression of the acceleration, we would get the following. So r square with r square would cancel, then it would be half m. Then the acceleration of an Atwood machine disk, in which the pulley is a disk, is given by the following: fractional mass multiplied by g. Now let's do application 1. We have a modified Atwood machine. The adjacent figure shows a modified Atwood machine. Frictionless forces are negligible. Give the acceleration A of the system in each of the following cases. So for a massless pulley, the acceleration of the modified Atwood machine is given by m1 over m1 plus m2. So if the pulley is massive, then we need to add I over r square. The modification would be injection of the mass of the pulley in the denominator. So part A, I over r square would be mr square, because here we're talking about a hoop, and the moment of inertia of a hoop is given by mr square. So mr square over r square, that would be m. Then the acceleration of the system would be given by m2 over m1 plus m2 plus m multiplied by g. Now if the pulley is the disk, then the moment of inertia is given by half mr square. So I over r square would be half m, and the acceleration would be given by the same expression, but instead of m, that would be half m. Now what about application 2? The adjacent figure shows a modified Atwood machine. Frictionless forces are negligible. The mass m to accelerate downward. Give the acceleration A of the system in each of the following cases. In part A, the pulley is a hoop of mass m and radius r. So first, let's recall the acceleration of such machines for a massless pulley. It would be given by m2, which is helping the motion, minus m1 sine theta, which is opposing the motion. Here we're supposing that it is accelerating along m2, which is downward, divided by m2 plus m1 sine theta. Now we're ready to implement the modification, which is injecting mass I over r square. Then in the case of a hoop, I is given by mr square divided by r square, that would be m, and the acceleration would be given by numerator invariant, whereas the denominator we would add an m. Now as for the denominator, the disk, that would be I over r square, which is half mr square over r square, that would be half m. Then the acceleration of the system would be given by the following expression. Instead of m, that would be half m added to the denominator. Now application 3, what about the following undefined Atwood machine? So the masses will be factored by sine of the angle corresponding angle, so m1 sine theta, m2 sine alpha. Here we assume that m2 accelerates downward, and the acceleration of a massless pulley would be m2 sine alpha minus m1 sine theta over m2 sine alpha plus m1 sine theta multiplied by g. We're gonna inject I over r squared because the pulley is being massive. In the case where it's a hoop, the inertia would be m and the acceleration of the system would be as follows. In the case it's a disk, the inertia would be half m and the acceleration of the system would be as follows. And now let's solve the following problem. A disk of mass capital M, which is 2 kg and radius 0.1 meters, is suspended by a rope of negligible mass as shown above. The rope is attached to the ceiling at one end and passes under the disk. The other end of the rope is pulled upward with the force Fa. The rotational inertia of the disk around its center is given by mr squared over 2. In part A, we need to calculate the magnitude of the force Fa necessary to hold the disk at rest. So the disk is at rest, we can use rotational equilibrium or translational equilibrium. Now let's utilize the forces that act on the pulley. Because the pulley at some point, we're interested in determining the torques around it, so we're interested in a rigid body diagram of the disk, which is the pulley itself. Now, what are the forces acting on the disk? We have the pull of gravity down, we have the tension Fa in the right portion, and we have the tension Fa in the left portion. Now here in this case, we didn't include the force acting at the pivot or at the axis of rotation, simply because we don't have the axis of rotation. Now here in this case, because the disk is at rest, we can say that simply Fa plus Fa should balance Fg because we're at translational equilibrium. And the tensions at both sides are equal because the disk is not rotating. Although the disk is inertial, but we said that the tensions along the disk or along a massive pulley, they are equal if the acceleration is 0, which is this case. So 2Fa would be equal to mg, then Fa would be equal to mg divided by 2. And the value of m is given by 2, g is given by 9.81, so Fa would be given by 9.81 newtons. Now at time t is equal to 0, the force Fa is increased to 12 newtons. So the minimum force from previous part A that is required to hold the disk at rest is given by 9.80 newtons. Now the force Fa is increased to 12 newtons, causing the disk to accelerate upward. The rope does not slip on the disk as the disk rotates. Calculate the linear acceleration of the disk. Now we need to implement the Newton's second law. Now let me repeat again what are the forces acting on the pulley. We have the pull of gravity down, we have the tension in the right portion, and we have the tension Fb in the left portion. Now why the tension in the left portion has been represented to be greater than Fa? Simply because the disk is rotating counterclockwise, so we need an unbalanced torque such that Fa is greater than Fp. Now remember that here also we don't have axis of rotation, so we're not gonna include the force at the pivot or the axis of rotation. Now let's apply Newton's second law for rotation. Torque net, first for translation, F net is ma, which means Fa plus Fb plus Fg is equal to ma, and taking the positive direction to be up, then Fa plus Fb minus mg would be equal to ma. And we're interested in searching for, here how many unknowns? We're interested in searching for A, but how many unknowns do we have? We have Fb and A, which means we have two choices to solve such type of equations. Either convert it to a differential one, and such type of dynamics would be challenging because we don't know what would happen at the end of the system, or to find another equation. The easy route is to find another equation by implementing Newton's second law for translation. That would be torque net is equal to I alpha, which is torque A plus torque B plus torque G equals to I alpha. Torque G produces no torque. Gravity produces no torque because gravity itself passes through the axis of rotation. Assuming that Fa and Fb are being applied tangentially to the disk, so the torque A would be FAR, torque B would be minus FBR. The moment of inertia of the disk is half mr squared multiplied by A over R. R with R cancel, that would be FAR minus FBR is equal to half mRA. R with R cancel, that would be Fa minus Fb is equal to half ma. And now we have two equations to solve simultaneously for A. Now we can add left members and right members, and we can see that FB's cancels, then the double of A is equal to 3 over 2 MA plus MG. Taking MG to the other side and isolating for A, we would have that the acceleration, linear acceleration of the disk is given by 1.46 meter per second square. Now in part C, they're asking us for the angular speed, and we know that the angular speed can be determined from the angular acceleration using kinematics. So first let's determine the angular acceleration, which is given by A divided by R, which is 1.46 divided by 0.1, and that would be 14.6 radians per second square. Since alpha is constant, then the type of motion is uniform varied circular motion, and we can use the following equation: omega is equal to omega 0 plus alpha t, because we know that they need the angular speed at a specific instant, which is t is equal to 3 seconds. If we're starting from rest, then omega 0 would be 0, alpha multiplied by t, so that would be 43.8 radians per second. And then that's it for me in this video, guys. See you soon in a new one.